Look at a crash frozen in time. In the exact fraction of a second where two objects meet, a complex physical exchange begins. A collision is a harsh mechanical event, but for a physicist, it is a strict mathematical transaction. The two bodies are rapidly trading physical quantities. The foundational rule that governs this trade comes from Newton's third law. It states that the force the first object exerts on the second is exactly equal and opposite to the force the second exerts on the first. Because these mutual forces are perfectly balanced, the total linear momentum of the system is always conserved. Linear momentum is the product of an object's mass and its velocity. If you add up the momentum of both objects before the crash, it will exactly match their combined momentum after. The equation delta P1 plus delta P2 equals 0 is a constant. You can see this transfer in a controlled environment like a felt table. Strike a cue ball into a stationary target ball of the same mass, and the cue ball stops dead. It pushes off the second mass, transferring its initial speed and momentum completely. But that mathematical perfection raises a question. If the system's momentum always survives intact, what happens to the kinetic energy? Kinetic energy is the energy an object possesses due to its motion. Linear momentum is a guaranteed mathematical constant. The kinetic energy's fate is the variable that defines the physical reality of the crash. To understand where the motion goes, we have to look closely at delta t. Delta t is the tiny interval of time, often just microseconds, during which the objects are actually touching. Collisions are not instantaneous switches. They unfold over this brief window. Visualize the deformation as an invisible spring connecting the colliding masses. As they press together, kinetic energy drops, stored inside the compressed spring as potential energy. In an elastic collision, the internal structure completely rejects permanent change. The spring compresses, then flawlessly rebounds. Because the spring snaps back to its exact original shape, the objects are pushed apart with their initial kinetic energy completely restored. No energy was lost in the transaction. True elastic collisions are rare, idealized events in our everyday world. You mostly find them at the subatomic level, or in the vacuum of space, where both momentum and kinetic energy are preserved. Step out of the idealized textbook and onto the road for a messier reality. Crumpled steel and shattered glass show us everyday collisions are destructive. Apply our spring model to an inelastic collision. The internal spring compresses, but suffers a violent bend. It warps, failing to hold its shape. Because the structure is compromised, stored potential energy cannot be fully returned as motion. It begins to leak away. The initial kinetic energy is transformed into other physical realities. It becomes the sound of impact, the heat generated by friction, or the permanent structural damage. The objects will still bounce apart, but they do so sluggishly. They possess less total kinetic energy exiting the crash than they did entering it. Inelastic collisions demonstrate a universal tax on kinetic energy. The physics of the universe exacts payment in the form of structural damage and dissipated heat. What happens when we push the concept of structural deformation to its absolute physical limit, absorbing the impact without any bounce? This creates what is known as a completely inelastic collision. It is a scenario where two masses collide and permanently stick together. In our analogy, the metaphorical spring compresses and then shatters entirely. Instead of pushing back, the broken pieces act like a permanent hook, fusing the two masses into a single block. This fusing of mass dictates the maximum possible loss of kinetic energy allowed by physics in a single system. The energy required to permanently bind the objects consumes the majority of their initial motion. Yet, even after this catastrophic loss of kinetic energy, the rule we established at the beginning remains intact. The linear momentum of the newly combined mass is perfectly conserved. This matrix categorizes the spectrum of collisions. Whether a collision is elastic, inelastic, or completely inelastic depends entirely on delta K, the change in kinetic energy, and how much motion survives that internal spring. Momentum guarantees the math of an isolated collision will always balance, but it is the kinetic energy